Okay, let's start. So good afternoon, everyone. So welcome to our tutorial on learned image and video compression with deep neural networks. I'm Dongxu from the University of Sydney. So today, my colleagues Guo Lu from Beijing Institute of Technology, China, and Zhen Yang from ETH, Switzerland, will present this tutorial. So I will also help them for the presentation, and I would also be happy to answer your questions during the Q&A session, which is at the end of this tutorial. So Ran, can you start?
Yes, sure. Okay, welcome to our tutorial. Oops, what's wrong? Sorry. The first part is learned image compression, will be presented by me and my advisor, Dr. Radu Timofte. And nowadays, there are increasing amounts of high-resolution images and videos over the internet. However, the limited bandwidth of the internet and the limited storage of our terminal devices makes image and video compression a very significant research topic. For example, I took this photo on the first day when I arrived in Switzerland. And because the scenery is very beautiful, so I took a very high resolution image. The resolution is 7,000 by 5,000, and so there are totally around 40 million pixels. If we do not have any image compression technology, the uncompressed image will occupy 120 megabytes. And even if I captured a video, and the things could be even worse. If the video has 60 frames per second, and the bitrate will be as high as 7 gigabytes per second. And if I captured an 18-second video, it will use up all of my mobile memory. And therefore, during the past decades, there were plenty of image compression algorithms. For example, if we compress this image with the lossless compression algorithm PNG, and the file size can be reduced to 1/3, 44 megabytes. And if we use the lossy compression algorithm JPG, and it can be further reduced to 9 gigabytes. Therefore, image and video compression plays an important role in multimedia streaming, online conference, just like what we are doing, and also data storage and etc. In this tutorial, we mainly focus on the lossy compression algorithm. A lossy compression is defined as the method to significantly reduce the bitrate with acceptable quality loss. And therefore, there is a rate distortion problem in image compression. This figure plots the rate distortion curves of some typical methods. The horizontal axis is the bitrate, and higher bitrate indicates larger file size. And the vertical axis is the quality. Higher quality indicates lower distortion. And therefore, for a specific image compression method, this curve is always an increasing function. That is, if we have higher bitrate and the quality can be higher. If we fix the horizontal axis, the curves on the top indicates better quality at the same bitrate. And if we fix the vertical axis, the curves on the left indicates lower bitrate at the same quality. Because rate and distortion is a trade-off problem in image compression. So these two things are actually equivalent. If we can achieve better quality at the same bitrate, it is equivalent that we can reduce the bitrate at the same quality. So the target to studying image compression algorithms is to move these curves towards the left top corner. And there are plenty of metrics to evaluate the compression quality, such as PSNR and SSIM are two commonly used objective quality measurement. And NEMA and LPIPs are more correlated to perceptual quality, and we can even directly use the user studies to measure the compression quality. And at the beginning of this tutorial, we briefly introduce the traditional image compression methods. The classical architecture is shown as this. In traditional image compression, the raw image is first transformed into the frequency domain, and then the coefficients are quantized to reduced bitrate. And the quantized coefficients are then fit into the entropy coding. Entropy coding is a kind of lossless data compression algorithm. And after the entropy encoding, we get the bit stream, for example, the JPG file. And at the decoder, we first restore the quantized coefficients from the bit stream via the entropy decoding, and then we inversely transform the quantized coefficients to reconstruct the compressed image. The classical standards are like JPG, which uses the DCT transform with the Huffman entropy coding. And later, we have the JPEG 2000 standard, which uses the wavelet transform and arithmetic coding. And the latest image compression standard is BPG, which is based on the intra mode of the video compression standard HEV-C. And this figure shows an example of the JPEG compression framework. The raw frame is first split into 8 by 8 blocks, and each block is then transformed by the DCT algorithm. And the coefficients are quantized given the quantization table. And then its DC and AC components are processed in different ways and then fit into the Huffman entropy encoder. And the decoder just do the reverse thing. Here we first introduce a preliminary of entropy coding. The entropy is defined as the expectation of information content. Information content is defined as the minus log of the probability. It means that if one thing is very likely to happen and its information content is low. For example, if I say that tomorrow the sun will arise in the morning and there's almost no information. But if one thing, the probability is low and its information content will be high. For example, if I say that tomorrow will be snowy and it is more informative. And this mathematical expectation can be expressed as the formula in the block. It is its probability multiplies its information content. And based on the entropy, we can define the cross entropy. In this formula, P and Q are two distributions, and the cross entropy is the cross entropy between these two distributions. According to the information theory, the cross entropy is always higher than the entropy, and their difference is called the KL divergence, which means the mismatching degree of these two distributions. Okay, given this algorithm, we see how arithmetic coding works. We use a simple example. Given this probability function, is that there are 60% chances of this sample to be neutral and 20% to be positive, 10% to be negative, and 10% to be end of data. If given this message, which has 3 elements, neutral, negative, and end of data, we first split the interval from 0 to 1 into sub-intervals according to this proportion, 60%, 20%, 10%, and 10%. Because the first element is neutral, responds to the first sub-interval, and therefore we pick up this sub-interval 0 to 0.6 out and further split it according to the same proportion. And the second element, negative, corresponds to the interval from 0.48 to 0.54, and we further pick it out and divide it according to the same proportion. The final element, end of data, corresponds to the interval of 0.533 to 0.54. And the last thing we need to do is to find a shortest binary number in this interval. In this case, it is 0.1301010. The first 0 can be discarded because it's always between 0 and 1, and therefore we need 8 bits to encode this message. And based on the arithmetic coding, there is an adaptive arithmetic coding. It means that we can change the frequency tables while processing the data. For example, after we encoded the first element, neutral, and we pick out the interval from 0 to 0.6, and now we can change to another probability table For example, it can be 50% neutral, 30% positive, and so on. And it can be changed from element to element. And let's go back to the cross entropy. If we define the Px as the real distribution of the data, and Qx is an estimated distribution, which can be an output from the neural network. And if we encode a message with our estimated distribution Qx, and the expected bit rate is theoretically able to be as low as the cross entropy with only a little bit overhead, and the compression is lossless. Okay, given this preliminary, let's go into the main part of this tutorial, is learned image compression. This figure shows a typical architecture of learned image compression. The X is the input raw image. It is uncompressed. And the encoder and decoder networks, GA and GS, are deep neural networks, which can be optimized jointly. And after the encoder network GA, we get the output Y, which is called a latent representation, which is similar to the DCT coefficients in JPEG. The latent representation is used to represent the information in the input image. And then we quantize this latent representation. And because we want to train the whole framework in an end-to-end manner, so we need to keep the gradient, and therefore we should use some differentiable quantization technologies here. And after the quantization, we get the quantized Y, and the quantized Y will go through the decoder network to get the compressed image. And here, R indicates the bit rate. According to the preliminary, the bit rate can be estimated as the cross entropy of the probability function, and the probability function is estimated via a differentiable entropy model. And the loss function is designed as this. Due to the rate distortion trade-off, the first term is the bit rate, and the second term is the distortion. The lambda is a hyperparameter to balance the rate and distortion terms. The distortion can be defined as the MSE or SSIM index, and so on. And we note that in this figure, there's also another network called GP, which is able to transform the input image to the perceptual space. However, in most of latest methods, this GP is just set to be identity. So in this tutorial, we mainly focus on this blue part. The first algorithm to introduce is the Ballet's ICLR work in 2017. It proposed a CNN transformer plus a factorized entropy model. The framework is shown in this figure. We can see that the encoder and decoder networks GA and GS are 4-layer convolutional layers, and therefore they can be jointly optimized. And the latent representation Y is quantized to Y hat, and Y hat will be entropy encoded to the bit stream. Here, if we just round Y to Y hat, the quantization is not differentiable, and therefore there will be no gradient. Therefore, they propose a noisy quantization method during the training phase. They add the latent representation Y by a noise delta Y, which is a uniform distributed noise with the mean of 0 and the width of 1. That is, it's a uniform distribution from -0.5 to 0.5. The reason for adding such a noise is that this noise is the same as the quantization noise. For example, if Y is 4.2, and after the quantization, the Y hat will be 4, and the quantization noise is -0.2. And because the number is randomly appears, so the quantization noise is a uniform noise, ranges from -0.5 to 0.5. And given this noise, the Y tilde, which is the sum of Y and this uniform noise, is able to simulate the quantization procedure. And the next thing is the differentiable entropy model. They designed the cumulative function as a composition of functions. The cumulative function is defined as the integral of the probabilities on the elements. The cumulative function is defined as the integral of the probabilities on the values smaller or equal than the current value. For example, the cumulative function of x means the integral of p and the values smaller or equal than x. And here the composition of functions fk and a circle of fk minus 1 and to f1, it is defined as this. It's defined as, for example, f1x and then f2 with the input of f1x and so on until fk. And therefore, if we want to make it as a cumulative function, it must be an increasing function with the range from 0 to 1. And these functions are defined as this. And to ensure that c is increasing, we have to ensure that each fk is increasing. And therefore, the derivative of gx must be positive and the matrix H must be positive. And therefore define H as a soft plus output, and therefore it is always greater than 0. And they define this A as a 10H output, and therefore it's always greater than minus 1. And because the derivative and because of the derivative of 10H is also in the range of 0 to 1, and therefore if we ensure that A is greater than minus 1, the derivative of gk is always greater than 0. And in this way, the fk is always an increasing function. And the final f capital K is defined as the output of a sigmoid to constrain this output number between the range of 0 to 1. And here the x can be either y tilde or y hat, depending on your testing or training. And given this probability model, we can estimate the bit rate as the cross entropy as mentioned above. And finally, the loss function can be defined like this. The first term is the bit rate, and the second term is the distortion. And this lambda is a hyperparameter to make a trade-off between rate and distortion. And because the whole network is differentiable, they have two differentiable convolutional neural networks and the differentiable quantization step during the training and the differentiable entropy model. This whole framework can be optimized in an end-to-end manner. And later on, they further propose a hyperpariah entropy model. In the hyperpariah model, they further transform the latent Y by the network HA to the hyperpariah matrix Z. And both Y and Z are quantized using the same method as before. And Z hat is encoded using the differentiable entropy model described before. They just use the factorized entropy model to encode Y hat. And Y hat is then transformed by the network HS to generate the probability functions of Y hat. Here they model the probability function of Y hat as a Gaussian distribution, and therefore the output of HS are the sigmas of these Gaussian distributions. Because this sigma depends on the hyperpariah Z, and therefore this probability function can be seen as the probability of Y conditioned on Z. And what is the advantage of the hyperpariah entropy model? Let's see this example. The matrix Y shown in the middle is the latent representation. If we just use the factorized model, we can see that there's still lots of structural information in this matrix Y. It means that this kind of spatial structural information are not captured, and therefore it will lead to the redundancy. Because the spatial correlation means there's still some spatial redundancy in this latent Y. And after we use the hyperparameter information, the right figure shows the number of Y divided by sigma, and we can see it is almost independent. And it means that the sigma, which are generated from the hyperparameter Z, is able to describe the structural information in Y. And therefore, using this hyperparameter, we can reduce the dependency in the latent Y, and therefore we can reduce the redundancy and to save the bit rate. And here we have to note that the hyperparameter Z also consumes bit rate, but in the experimental results, it is showing that the reduction of the bit rate on the latent Y is greater than the overhead of the bit rate of Z, and therefore it benefits the image compression. And after this work, they further proposed an autoregressive entropy model. The motivation of autoregressive model is that we can not only use the hyperparameter Z to capture the dependency in the latent Y, but there are also dependencies inside the matrix Y. That is, the elements in the matrix Y can also be correlated, and therefore they designed a context model with the input of the previous elements in the matrix Y. Here, Yi is defined as the element with the index of I in the matrix Y. And this context model takes its previous elements to generate the probability function of the current element. Let's see the details. Due to the chain rule of the conditional probability, the probability of the matrix Y can be rewritten as the multiplication of this conditional probabilities. That is, the probability of Y1 multiplies the probability of Y2 in condition of Y1, and the probability of Y3 in condition of all its previous elements, and so on. And therefore, this conditional probability Py given Z can be rewritten as the production of Pyi given all its previous elements and Z. And in this method, they also modeled this probability function as a Gaussian distribution. And we can see that the mu and sigma elements, mu and sigma of these Gaussian distributions comes from not only the hyperparameter Z hat, but also the previous elements in the latent Y. And how to implement this context model, we can use a mask CNN. For example, now we want to model the probability function of this element of this element Yi, and we can use a mask CNN. The first layer of the mask CNN is shown here. In the kernel, only the previous elements are set to 1, and the weight from the current and following elements are all set to 0. In this way, the output of the first layer in this position only depends on its previous elements. And from the second layer, because the output from the first layer at this position only depends on its previous element, so that from the second layer, the central weight can be set to 1. And we can also ensure that we only use the information from previous elements. And follow this way, we can also construct the 3D mask CNN. Okay, and up to now, we introduced the 3 kinds of entropy models: the factorized one, the hyperparameter, and the autoregressive model. And this autoregressive model actually is a joint autoregressive and hyperparameter model. And at the same time, there is another autoregressive method, which was published almost the same as at the same time as the previous method. And the idea is also similar. This unseen area indicates the following elements, and therefore they only use the previous elements in the matrix Y to model the distribution of the current element. The idea is just very similar to the previous method. Okay, and now I use a simple example to help you easily understand these three entropy models. For example, we have a matrix Y, which has three elements, Y1, Y2, and Y3. And each of this indicates what I drink in these 3 days. The options are hot coffee, hot tea, cold coffee, and cold tea. If in the factorized model, they just assume that they're assumed to be independent, and therefore we need 6 bits to encode the matrix Y. And in the hyperpariah entropy model, given the hyperpariah, for example, the Z is the temperature of these 3 days. And given this hyperpariah, we can model the conditional probability. For example, if we know that if the temperature is less than 20 degrees, and I only drink hot coffee or hot tea, and with the same probabilities as 50%. And if the temperature is higher than 20 degrees, I only drink cold drinks. And in this way, the entropy is reduced to 1 for each element. And therefore, we can encode the matrix Y with only 3 bits. And if we further have an autoregressive model, we can further capture the correlation between the different elements in the Y. And for example, here we make an assumption that I don't drink coffee or tea in 2 consecutive days. That is, if I drink tea in the first day and I can only drink coffee in the second day. If we have such kind of correlation between the elements in the matrix Y, and there are only 2 options, and the entropy of the whole matrix Y is reduced to 1, and therefore I can only use 1 bit to encode the matrix Y. And we can see that in this simple example, the bit rate can be reduced by 6 times from the factorized to the autoregressive entropy model. It is because that we made some very strict restrictions here. For example, in the cold weather, I strictly not drink cold drinks and only drink hot drinks. And it is very strict that I don't drink coffee or tea in 2 consecutive days. But in the practical scenario, it may be different. For example, in the practical scenario of image compression, from the factorized model to the joint model of autoregressive and hyperpariah model, the bit rate of an image can normally be reduced by 20 to 50%. Okay, and then I introduced some alternative strategies used in the learned image compression algorithms. The first one is another kind of differentiable quantization method. In this reference paper 4, they use another kind of quantization method. Instead of quantize the continuous value to the integer, they predefine some centers, and they quantize the input value to the nearest center. And during the training, they define such kind of a differentiable quantization method. In this kind of quantization, the result will be like this. In the inference, it will be quantized to the given centers, and in this differentiable ones, it will be something like this. It's a soft quantization, and it is differentiable. And then they further use another trick, is to define a Z bar. The Z bar is implemented by TensorFlow like this. What does it mean? It means that the first part of gradient is stopped, and therefore during the forward process, the value of Z bar equals to the value of Z hat, because in the forward process, the stop gradient doesn't work, and it just equals to the value of Z hat. It means that in the forward process, they just used exactly the same value of the as the inference phase, not only the simulated value. And during the error back propagation, because the first part has no gradient, and therefore the gradient of this z bar is just the same as the tilde z, which is the differentiable quantization. And the next strategy is an important map, because in the image, there are different regions, and in some regions, such as the background, its texture is very simple, and therefore we can allocate fewer bits in the background. And for example, in the edge or some sharp areas or areas with complicated texture, we have to allocate more bit rate. And therefore, we can learn an important map to reasonably allocate the bit stream. And how this map works, given this as the latent representation, if this green area is an important area and all of these channels will be maintained. And if it is learned that this blue area is less important, for example, if it has less complicated texture and only a few channels will be maintained and others will be set to 0. And in this way, we can reasonably allocate the bitrate in the image. And the third strategy is to use the Gaussian mixture model for entropy. Because just to use a single entropy model, it is not very flexible to model the probability function. And therefore, in the CVPR 2020, Cheng et al. Proposed to use a GMM model, which is the sum of several Gaussian distributions, and it is able to more flexibly model the probability function. Okay, and this is the latest CNN-based learned image compression methods. It's called a coarse to fine model. We can see that they use hierarchical latents. They further transform the latent to a higher level latent, and then to a third layer of latent. And in this way, the probability functions can be modeled better and reduce the rate distortion performance. For example, if we also assume that the first layer of the latent is what I drink every day, and the second layer of latent can be the temperature, and the third layer of the latent may be the weather. It can further provide the hyperpariah information to encode the lower level hyperpariah information. And this shows the performance of this learned image compression methods. It can be seen that the latest learned compression methods, especially the context methods and the coarse to fine methods, already outperform the latest traditional image compression standard BPG. However, on the different data sets, the rank may vary on different data sets. For example, in these two figures, the red curve is always on the top, but on the left figure, the green curve is on the top of the blue curve. But on the right figure, the blue curve is on the top of the green curve. This indicates that the learned compression methods may depend on the training data. And it is not only a kind of, we can say it's a kind of shortcoming, or it's a kind of point of the learned compression method, but also it happens on all machine learning methods. It means that the generalization capability of learned methods may be not as stable as the traditional handcrafted methods. Okay, and the next part we go to the variable rate image compression methods, and in all above mentioned methods, they have to train each model for each point. For example, there are 10 points in the red curve, and they have to train 10 models to achieve each operating point. And And if we consider if it is possible to train only one model to achieve variable rate of image compression, the first kinds of methods are the RNN-based methods. The basic idea is like this. The input patch is first transformed via an encoder and decoder, and we got the output patch. And then we calculate the residue of the output patch. And then we further input this residue to the second iteration and further encode this residue. And there can be n iterations, and the output patch will have higher and higher compression quality during the iteration increases. And we implement it by using the recurrent cells between the iteration to iteration. For example, and we can just stop it at the target bitrate. For example, if we want to compress this input patch with 16 bits, and we can just stop at the fourth iteration. And later on, there's an improved version with deeper encoder and decoder networks. For example, they use 3 RNN cells in the encoder and 4 RNN cells in the decoder to improve the rate distortion performance. And recently in the CVPR 2018, there's another kind of recurrent-based methods. The key idea is similar to previous, is that they still first reconstruct the image and then calculate the residue and then further encode the residue. And they also proposed an advanced version by increasing the depth of the neural networks. And another kind of variable rate image compression is a conditional autoencoder. We can see that this framework is very similar to the CNN-based framework. And the loss function is also the distortion plus lambda times bit rate. And lambda is to balance the rate distortion performance. And therefore, changing the values of lambda will lead to different operating points. So in the conditional autoencoder, they input this lambda together with the image to the encoder and decoder networks. And therefore, the encoder and decoder networks can be seen as conditional networks. That is, they can compress the image with variable bitrate according to the input lambda. And given this lambda, the loss function became as the sum of the rate distortion performance on all possible lambda values. And to make the compression method more flexible, to make it more flexibly to achieve variable bitrate, they also changed the quantization step. We know that a smaller quantization step leads to higher bitrate, and larger quantization step leads to lower bitrate. And therefore, the change of the quantization step can also lead to different bitrate. And combining the conditional autoencoder and the quantization step, they can more flexibly achieve variable bitrate image compression. And the loss function is like this. It's also the sum over all possible lambda values and all possible quantization steps. And this is an ablation study. It shows that changing the lambda, in this figure, different curves indicates different lambda values. It can be seen that changing the lambda is able to change the bit rate. And also in each lambda, changing the quantization step can also achieve variable bit rate. And the most important thing is that they only need to train one model instead of several models to achieve different bit rates. And this shows the compression result. It can be seen that their rate distortion performance is just slightly worse than the red curve. But in the red curve, they train different models for different operating points. And in this method, they just train one model for all of these bit rates. It can significantly save the training time and also the memory to store the pre-trained models, but only with slight degradation of the rate distortion performance. And another way is to use a wavelet-like transformer. This wavelet-like transformer is an invertible transformer. It is different from all previous methods that the encoder and decoder are not invertible in previous methods, but in this method, they are invertible. The advantage of using an invertible transformer is that in this way, the quantity loss only comes from quantization. If I do not quantize the latent, and there will be no quantity loss, the input x will be exactly the same as the output tilde x. But in previous methods, because the encoder and decoder networks are just convolutional neural networks, they are not invertible, and therefore in previous methods, even if I do not quantize the latent, they cannot achieve a lossless compression. And therefore in this framework, because of the invertible autoencoder, they can achieve not only variable bitrate, but also lossy and lossless compression by only one framework. And let's go into the details of this network. The input are first split into two parts according to its index. The pixels with even index are split into this set XE, and with the odd index are split into this set XO. And P1, U1 to Pn, Un are convolutional neural networks. But because of this kind of design, if we ensure that the networks P1, U1 until Pn, Un are the same as those in the decoder side, and this network can be invertible. And because image data is a kind of two-dimensional data, and therefore they need to use a two-round split. The first round is row-wise, and second round is column-wise. And they can split the input image to 4 bands called LL, HL, LH, and HH, similar to the wavelet transform. And given an input image, they transform the image into this kind of 10 bands. It can be seen that S1, S2, S3, and S4 are the subband divided from the L in the higher layer. And these 10 bands are compressed with the entropy model. They use a recurrent autoregressive entropy model. And this shows the compression result. It can be seen that they first train each model for each point, and they achieve the best result, shown as the blue curve on the top. And they can also achieve variable bitrate by training one model for all points, shown as the blue curve with triangular mark. And furthermore, they also can train one model for both lossy and lossless compression. Okay, and the next part is the generative image compression. The framework is like this. The generative image compression aims at compressing an image with very low bit rate, but with a photorealistic output. And this is the basic framework. The encoder is the same as before, and the decoder here is also a generator. And they also add a discriminator to make the decoder the generator to generate the photorealistic output. And the loss function is designed as this: is a combination of the gain loss and the ridge distortion loss. The gain loss is to ensure that the output is photorealistic, and the ridge distortion curve is to ensure that is to constrain the ridge distortion trade-off. And there are two hyperparameters in this loss. The first is the lambda, and the second is beta. And they can change the weight of different terms to balance three things. One thing is how photorealistic it is, and the second thing is if it is with high fidelity, if this lambda increases and the weight of the objective distortion increases, and therefore the output image will have higher fidelity to the input, but maybe with lower perceptual quality. and the beta controls the quality and distortion. And this is a user study of these GAN-based methods. The horizontal axis indicates the bit rate, and the vertical axis indicates how many users prefer the GAN-based methods than the BPG methods. And in this user study, the bit rate of the generative compression method is fixed. For example, in the left figure, the bit rate of the generative compression is fixed as 0.033 BPP, and they increase the bit rate of BPG to see at which point half of the users prefer each of these methods. And in this point, it means that they have the same perceptual quality. And we can see that in the left figure, when the bit rate of BPG increases to 0.065, half and half people prefer the generative methods and the BPG methods, and they have the same perceptual quality. It means that the generative method is able to achieve the same perceptual quality as BPG with almost a half bit rate. And this shows an example of the compression result. It can be seen that in the generative method, they only use less than half BPP of the JPEG of BPG, but has more visual pleasing compression results. But here we can also see the problem is that in the generative method, because we use a GAN network, so some contents may be changed. And although the output image is visual pleasing, but some contents are very different from the original image. And based on that, the further proposed and advanced version is also to input the semantic information to the discriminator. And then the discriminator becomes a conditional discriminator. And they also generate a binary heat map M here based on the semantic information. The function of this M is to zero out some information. For example, in this X, if I only have low bandwidth to transmit this image, and I do not care too much about the information of the car, and I can mask the bit rate corresponds to the car to reduce the bit rate, and the information of the car are completely generated by the generator. This shows an example. We see from this figure, there's no synthesis. It means that all bit rates are input to the generator. And for example, in this figure, the information of people are zero out, are masked by the binary map, and therefore they can reduce the bit rate by 33%, but the information of the people are just randomly generated by the generator. Okay, and as mentioned before, the problem of this method is the low fidelity. That is, the generated image, although it is very visually pleasing, but it can be very different from the input. And later on, there is a high fidelity generative image compression method, which increases the fidelity of the output image. It means that the generated image looks very similar with the input image and also has high perceptual quality. The key point here is use a conditional discriminator. That is the discriminator conditioned on the latent Y, because Y contains a lot of information of the input. And they input this information Y to the discriminator, makes the discriminator to determine if the output X prime is photorealistic, and also whether it is whether it has high fidelity to the input image. And the loss function they use is very similar as previous. but the only difference is that the discriminator now is a conditional discriminator. And this shows the result. We can see that in this Hi-Fi-C method, they can use less than half bit rate of BPG to achieve the output image with more texture details and more visual placing. And also here, the example of this hair. Okay, and let's make a conclusion of the previous methods. We introduced the CNN-based methods with the factorized entropy model, which models the latent information as the independent identity distribution, and the hyperpariah entropy model, which further generates a hyperpariah matrix Z to provide some spatial information to reduce the entropy of the latent Y. And also the autoregressive entropy model to further capture the correlation between the elements in the matrix Y. And the coarse to fine entropy model, which have several layers of hyperpariah information. And the conditional autoencoder with the input of the lambda to achieve variable bit rates by only training one model. And also the invertible autoencoder, which is able to achieve both lossy and lossless compression by learning one framework. And the RNA-based methods mainly targets to achieve variable bit rate. And the GAN-based methods can achieve photorealistic compressed image with very low bit rate. And as shown before, the results shows that the state-of-the-art learned image compression methods successfully outperformed the latest traditional compression standard BPG. It shows that this topic of learned image compression is a promising direction. And the question is, will the learning-based compression be standardized? Because all of the current existing standard of image compression are handcrafted traditional methods. And the answer is yes. The JPEG recently initiates the standardization of image compression based on AI. It was agreed that there's a strong evidence that learning-based image coding solutions can outperform the already defined anchors in terms of compression efficiency when compared to state-of-the-art conventional image coding architecture. And thus, it was decided to create a new standardization activity for the JPEG AI on learning-based image coding system, so that we hope we can have a learning-based image compression standard in the near future. And the second question is, can learning-based methods be compatible with the traditional standard? It is an interesting question because currently, if we are viewing images on our mobile phone, iPad, or personal laptops, the image viewer can only decode the standard bit streams such as JPG or PNG and so on. And if we want to implement the learning-based methods, and if we want to make them practical, we have to download and install the pre-trained models, at least the pre-trained decoders to our mobiles. But currently, we don't have such model on our mobile. So is it possible to make a learning-based methods be compatible with these traditional standards, especially with the traditional decoders? And we have made an attempt. In this ECCV workshop, we proposed methods to improve the image compression without changing the standard decoder. We can see from this framework that the bit stream can be decoded by the standard JPEG decoder. And what we do is at the encoder side, we learn an attention network to generate the attention map. And the attention map element-wise multiplies the DCT coefficients, and therefore it can be seen as a kind of frequency domain pre-editing. It pre-edits the image to be more easily compressed. And we also learn a quantization table different from the fixed quantization table in the JPEG standard, we learned the quantization table to improve the rate distortion performance. And all other encoding pipelines are just following the standard JPEG algorithm. And therefore, the bit stream can be compatible with the standard decoder. And we can see from this figure that the rate distortion performance of our method outperforms the JPEG method. We evaluated on PSNR, SSIM, and LPIPS. The LPIPS is more correlated with the perceptual quality. Is that it shows that we can improve the rate distortion performance with the standard decoder, especially at low bit rates. And in conclusion is that we achieve better performance without changing the standard decoder. And therefore, the compressed image by our method can be decoded and can be directly viewed on any common device, such as your mobile, iPad, or personal laptop, and so on. And these are the open source codes of the methods mentioned in this tutorial. The first one is an official TensorFlow implementation of the Bayes networks. It includes the factorized and the hyperpariah entropy models. And the second is an unofficial PyTorch implementation of the factorized hyperpariah and also the autoregressive models. And in the last, this generative compression method is also included in the in this GitHub directory as a kind of official TensorFlow implementation, because this work is also done by Google, so they just put them together. Okay, and now it's time for questions and answers. Thank you for your attention.
If you have any questions, you can use the chat. You choose the chat. You can use a button. You can put in the text chat, and then of course you can also directly speak to us. It's also fine. Yeah, you can also use the chat function in Zoom, and then after we say your question, we can answer your question. Okay, the first question is, where can I possible to get the slides from you?
That's a good question. I will upload it to my personal website. I can put it. I will upload it later.
I think the organizers also distribute the PPT slides to attendees, right? To the VCIP.
Yes.
Yeah. Okay. Okay. You can also upload it to your website. Okay. The second one is what are the advantages of modeling a network with lossy and lossless compression?
Yeah, it's an interesting question because in the traditional image compression method, such as JPEG, they use the same framework to because the DCT transformer is invertible, and so that in theory they can achieve both lossy and lossless compression in one framework. But in the learned compression methods, the autoencoder and the decoder are just neural networks, and therefore it's not possible to achieve lossless compression in one framework. And the advantage to achieve lossy and lossless compression in one framework, I think the first is that it also ensures that we can achieve a very high bit rate, because we can assume that in the if the autoencoder is not invertible, and it is not possible to achieve very high bit rate, because the output image is very hard to be ensured to be very similar to the input. And if we can use one framework from lossy to lossless compression, and we can very flexibly achieve a very large range of bit rates. And also we can, if we can train just one model for both lossy and the lossless compression, we can also reduce the training time and the memory to store the pre-trained models.
I think there are some works on they can learn a model that can adapt the bit rate. Say you have the scalable coding. Once you have more bit rate, once the bandwidth is good, then you can simply they can simply use a better model. They have adaptation module. I think there are some works on bit rate, variable bit rate coding, which means you use a very simple model without too much complexity, and then you can adapt your model from maybe from the low bitrate one to a high bitrate one, or from high bitrate one to a low bitrate one. So in this case, when the bandwidth condition changes, your model can adaptively can quickly change, and which is adaptive to the bandwidth change. Lugo, do you know such of? Can you give some reference to such works? Yeah.
I will give some slides.
You can put in the chat box. Yeah, you can add some. But I'm not aware of where there's some works that can the model can adaptively change from lossless to lossy model. I'm not aware of that. Yeah. But definitely you can use a very high quality. You can use a model to support different quality of lossless compression. Yeah, maybe high quality or low quality, different bit rates. Any other questions from the audience? Okay. Do we need to use different loss function for a model with lossy and lossless compression, or do we need to concatenate these loss functions?
Yes, for lossless compression, the loss function will be only the bit rate, because in lossless compression there's no quality degradation. So if we want to train a model with both lossy and lossless compression, the loss function will be designed as the sum of several individual loss functions. Does it make sense? It will be a sum of the loss function for lossy compression and the lossless compression.
But I think currently the ways to do lossy compression and the lossless compression are totally different, right? I think my group is also doing lossless compression. They use totally different approach.
Mm-hmm.
They try to model the context. Yeah, I think one of my students, Chris, is working on this direction and submit a paper to TIP. But I think he's not working on the Google's work. He didn't use the three classical works from Google. He used a totally different context model to do the directly do the entropy model and entropy coding, without using the networks to do the DCT part, to model the DCT part. I think, yeah. So I think there are totally different technologies. In this case, of course, since we did not use the model from Google, the three typical models from Google. So I think the solutions are also quite different. Yeah, I think use the context model to do this compression. Yeah.
Yeah, and in this method, this network follows the idea of the wavelet transform. So this method can be seen as a re-implementation of JPEG 2000 by deep neural networks.
Mm-hmm.
It just changed the filters in the wavelet transformer to neural networks, and changed the entropy coding to a differentiable entropy model.
Mm-hmm.
Yeah, so the theory behind it is very similar to JPEG 2000.
Mm. Yeah. Do you have any other questions? How about the standard? You talk about the standard efforts, right? So the companies are interested. We are currently working with internet company in China. They are also heavily involved in this direction because this deep learning based approach will be seems that deep learning based approach will be standardized in the next 2 years. How do you?
Yes.
What's your point of view? The possible directions. Say we will still continue to follow the three classical works from Google and try to improve the efficiency and the compression performance, or we should develop new frameworks which can beat the Google's framework. What's your point of view?
Well, in my understanding that in the standard, if we want to standardize the learned algorithm, I think there are more things to consider than the Google method because the Google methods and also some following methods are only evaluated on the codec image set. And the codec set only has 24 images, and therefore their generalization capability cannot be ensured. But if we want to make it as a standard, we have to make that at least it can be generalized to most of the images, natural images.
Yeah, I think that when they come to the standards, they will do more comprehensive evaluation of different approaches.
Yes.
A larger data set.
Yeah, at least on a larger data set, yeah.
There is another question from the audience about the lossy compression. Is the question is very long? Can you read by yourself and answer the question? Yeah.
Does the existing model need to be retrained for each image type? I think yes, because that is the point for all machine learning algorithm, not only in compression, I think, because this kind of data-driven methods heavily depends on the training sample. If the training sample has more diversities, and it can be generalized on more data sets, on more kinds of image.
Yeah, perhaps you can have a more pre-trained model based on the natural images, and then you can adapt this model. You can fine-tune this model based on the hyperspectral images or maybe remote sensing images or medical images. Yeah, you can do that because I think in our TIP work, we submit the work to TIP, we use the same strategy. Yeah, we train based on the data set used in Google's work. Then we fine-tuning our pre-trained model by using the images from by using the remote sensing images and medical images. Yeah. I think there is another question before this one. It asks it seems the lossy compression we need to predict the distribution for raw image in MSE optimization. For lossy compression, we also need to predict the distribution of the image in a Gaussian optimization. So which means that theoretically the learned models of lossy and lossless compression can be used or just fine-tuned. I think, Guo, are you still here? I think the approaches are different, right, Guo? Guo. I think in our TIP submission, when we come to the lossless compression, we use the work from ETH, try to use the context model. We do not do the DCT transfer. We do not different with the lossless one. Yeah. Chris,
and for the audiences, I think
Chris,
Chris,
you
can just.
Chris, are you here? My student Chris, are you here? Can you try to help?
You can just.
Yeah,
I think you can just unmute and just speak. Chris.
Yes, can you say something? Yeah, you can just unmute it and see. I think you are working on this direction, right? So can you give some comments here?
You are muted now, Chris.
Okay, yeah, okay, yeah. If you want to, okay, you can just type here. Okay.
In my opinion, I think the bridge work that also use lossless compression, because if you want to compress the feature extracted from the image, you have to use lossless compression, right?
Yeah,
So
once you do the feature extraction, you can never go back, right? You can never go back.
But the step that you want to compress the feature is a lossless compression, right? So I think they share similar architecture, but from Fabian's work that they use I think three-layer context model, which is more effective.
Yeah. So. Yes.
No, but I think if you do the feature extraction and then you want to reconstruct the image based on the extracted features, you can never get the perfect. You can never get the lossless reconstruction, right? Because you lose it.
Yeah, but we can get a perfect feature.
Yeah, you can perhaps for features you can do the lossless compression for features. Yeah. But you have to, once you extract features, you have to go back to do reconstruct the image based on the compressed and decompressed features. In that case, you cannot get the lossless reconstruction. Because you really lose information when you do the feature reconstruction. Yeah, when you reconstruct your images based on the features. Yeah.
Yes, and Chris, yes, you are right. The lossless compression is used to predict the distribution of raw image, but if we have an invertible transformer, and we can also encode the latent representation for lossless compression, because if we don't quantize the latent, and the latent can be inversely transformed to the lossless image. And in this way, we can also use the transformer not only can predict the distribution of raw images.
Okay. Any other questions from the audience? Yeah. Oh, okay. Okay, so if we don't have questions, then we can have a break. So we can have a 30 minutes break, and then we come back 30 minutes later, and then Lugo will present the second part. And then at the end of the second part, you can ask more questions. Okay, thank you. I'll see you 30 minutes later. Well, half an hour later. Okay. Bye.
I created a temporal GitHub directory and I upload the slide here. The link is in the chat box.
Okay, let us come back and restart. Go, are you ready?
Yep. So can you hear me?
Yes, please
Okay.
go ahead. Yeah.
Okay. Hello everyone. Welcome to our tutorial, Learn the Image and Video Comparison with Deep Neural Network. I'm Guo Lu from Beijing Institute of Technology. So this tutorial is co-organized with Dongxu from University of Sydney and Ren Yang and Radu from ETH Zurich. So in the previous slide, Ren Yang has gave a tutorial for learned image comparison. So in this tutorial, we will focus on the learned video comparison. And so in this tutorial, I will first introduce some basic knowledge for video comparison, since the audience of VCIP are somewhat familiar with video comparison, so I do not put too much attention in this section. Then I will focus on the low latency coding, which is end-to-end learned P-frame video comparison. Considering most of the current works can be categorized in this field, so I will give more detail in this section. So first, I will introduce the hybrid coding framework in learned video comparison, and then introduce the how to use the RDO technique in the inference stage. Since the motion is very important for video comparison, I will also discuss how to enhance the motion estimation and motion compensation for learned video comparison. Finally, we will also discuss the multiple reference frame for learned video comparison and discuss how to use this information to improve video comparison. And then I will give some example about how the learned B-frame comparison in recent publication. And then after that, I will introduce the autoencoder-based video comparison. Finally, I will show some experimental results on the benchmark dataset, and also some our recent open source project. So, okay, first for the background for the video comparison. Video comparison is a fundamental techniques to reduce the redundancy in videos and has been widely used to reduce the transition boundaries of the storage. So in the past decades, a lot of codec has been proposed. For example, the H.264 and the H.265 are the most widely used video codecs. And recently, H.266 has been finalized in 2020. And it is the state-of-the-art video codec. Although a lot of new techniques or proposal has been proposed in the mainstream codecs, they still rely on the handcraft technique to reduce temporal spatial redundancy. And recently, we have the deep learning techniques are becoming more and more popular and has been successfully applied to a lot of image and video processing tasks such as super resolution or denoising. So considering its powerful representation ability, it is feasible to apply the deep neural networks to video comparison. So in this section, I will first give a basic introduction for the hybrid coding framework used in the traditional video comparison. So first, given the input frame ST, we perform the prediction step. In this step, we will use the block-based motion estimation to get the motion vector between the previous frame and the current frame. Then we will use based on this estimated motion vector, we use the motion compensation procedure to warp the previous frame to the current time step and get the predicted frame and the corresponding prediction residue. So now we have the residual information. Then in the transform stage, we will transform the residual to the frequency domain from pixel domain to the frequency domain, which is easier for comparison. So usually we will use the DCT transform. And after that, we can get the reconstruct residual information. Here it's RT head. Then based on the predicted frame ST bar and the residual information RT head, we can get the reconstruct reconstruct frame, which is ST head. Then I will talk about how to use this hybrid coding framework for the learned video compression. So first, I will introduce our recent work on VCIP2019. We propose the DVC framework for learned video compression. As far as we know, this is the first end-to-end optimized video compression system. So the left panel is learned video. It's the traditional video compression approach. We can find that first we use the OptiFlow network to replace the original block-based motion estimation. Then then based on the motion, then since the OptiFlow has much data when compared with the block-based motion vector, so we need to compare the motion, the OptiFlow information before we send them to the decoder side. So now we use we use the autoencoder style network to compare the OptiFlow information. Here, the decoder has a four-layer convolutional neural network, and then the decoder uses a similar architecture, and both the encoder and the decoder use GDN and RGDN as a nonlinear function. So it should be mentioned that in the traditional video compression, the motion vectors are compressed losslessly, but in our approach, the OptiFlow information will be compressed in a lossy function. So this is a difference. Then after the motion compression, we need to get the predicted frame. So we replace the motion compensation with by using the motion compensation network. Here we rely on the previous reference frame and the motion information as well as the warped image. Since the warped image has some artifact due to the inaccurate motion information or the motion compensation, so we need to refine the warped image before we send them to the following steps. So here we use UNet style network to refine the motion, the warped image. Finally, we can get a predictive frame ST bar. So here, the network architecture uses some red blocks and error pooling to improve the performance. Then, once we get the predicted frame, we can get the residual information. In our approach, we also follow this prediction transform procedure, and we use a powerful and more complex residual compression network. In the traditional video compression, previous method just use the DCT transform or DWT transform to transform the residual from the pixel domain to the frequency domain. Now we use more complex neural network to transform the residual to latent space. Here we follow the previous work in RCLR 2018, where hyperprime model is used to compare the residual information. We use several convolution layer and also use a hyperprime network to estimate the mean and variance for the probability model. After that, we need to estimate the estimate the bit rate for the whole network. So in the DVC framework, there are two components that need to be sent to the decoder. They are the motion feature MT head and the residual feature YT head. So here we use a cumulative to estimate the probability model. Then we use entropy to then we can calculate the entropy, which is used to approximate the bit rate. So the definition was a cumulative in our approach. It follows the previous work and use several nonlinear and linear function to get the cumulative for the current feature. So now we can then we have to discuss the quantization. So since quantization itself is non-differentiable, so in order to optimize the whole model in an end-to-end fashion, we need to approximate in the training state. So in this approach, we also ending the uniform noise to approximate the quantization procedure, but in the inference state, we directly use the rounding operation. So finally, we can use rate and distortion laws to optimize the whole system. So now the lambda determines the trade-off between distortion and rate. Okay. So as I just said, that the DVC framework is very flexible because we can use the existing network to replace the component in DVC framework, and then we can maybe have a better compression performance. So in our journal paper, we also use the advanced encoding model for bit rate estimation with autogressive price, and we also use the motion and residual refinement model for the motion decoder and the residual decoder side to reduce distortion. As we know that the motion compression or the residual compression are lossy, so there's some distortion in this procedure. So we introduce the motion and the residual refinement modular to get more accurate motion and the residual information. Then I would talk about the variable bit rate solution. In our approach, so since the model is optimized by using a rate and distortion trade-off, so we have to train different model for different bit rates. For example, if we want to compress the image video with a different bit rate, we need different model with different lambda. So how to handle this problem is also very important. So in this paper, we also introduce an adaptive quantization layer, which can transfer the feature between different bit rates. So the solution is very simple. I think first we will train a basic learned image compression method. I think this approach can be easily extended to the learned video compression. So we just take a image compression with as an example to show our approach. So first, we will train a basic learned image compression network. Then we will fix the parameter and integrated the adaptive quantization layer into our approach. The network architecture of the adaptive quantization layer is shown in the right part. So it's we use a very lightweighted CNN network to implement our network. So after that, we can train the adaptive quantization layer using different quantization, using different lambda, and finally we get a basic model and several adaptive quantization layer with 4 different lambda. So now it's more effective to transfer or to storage our model for different bit rate. Here we provide some experimental results for our end-to-end learned p-frame compression. So we provide the experimental results on the GCT-VCD set, and we use the X264 or X265 as our anchor algorithm, and we compare with we also compare with the other learned video compression method. And the experimental results show that we can outperform the H264 by large margin and achieve compatible performance with the H265 in most data sets. Okay, now let's talk about the RDO technique. So as we know that the RDO is a fundamental technique for video compression. So in the traditional video compression pipeline, RDO is used to select the optimal mode for each coding unit. For example, the block size of each coding unit is determined by using the RDO technique. So, however, in the existing learned video compression framework, we only use the rate distortion loss in the training stage to optimize the whole model, while in the inference stage, we directly use a fixed model to compress the image or videos. Basically, it can be considered as that the modes are fixed after the training procedure, and the existing learned video codec cannot adapt to different video content as the previous traditional method. So how to handle this problem and how to apply the RDU technique in the learned video compression. So here we give two solutions. First, we can directly optimize the encoder, and second, we can create more modes and then select the optimal mode for each frame based on the RD cost. So now we first introduce how to directly use RDU techniques. So in the paper published in ECCV 2020, we propose an online encoder updating scheme. So here is an overview of our proposed scheme. So first, we will fix the decoder fix the decoder of our baseline method. Then we will update the encoder based on the rate distortion trade-off. I mean the rate distortion loss by using based on the rate distortion loss. Then after several iterations, the encoder is updated, and this encoder is adaptive to the input frame, and which means it has much better performance. So for each input image or each input frame, it will generate different encoder, but it should be mentioned that the decoder are fixed in our inference state, so it doesn't increase the computational capacity in the decoder side. So here we provide some visualization results for our online encoder updating scheme. So here figure A and figure B represent the reference frame and occurred frame, while figure D represents the changed feature after the updating procedure, while figure E and F represent the motion information. We can find that the motion information now has much more detail than previous. So basically, we has a nearly 0.7 dB improvement in terms of PSNR, and also the BPP drops about 9%. So this technique is quite effective for adapt the image for different content. So now another thing that I want to mention is the error propagation problem. So for the interpretation coding scheme, the compression of current frame ST rely on the previous frame ST-1. So however, the previous frame is lossy compressed, and the reconstruct error from previous frame will propagate to the current frame, which will decrease the compression performance. So as shown in the right figure, the blue line represents DVC baseline. It is observed that the PSR of the reconstruct frame drop as the frame number increase. So the reason for this phenomenon is that we do not consider the error propagation problem in the training stage. So now, how to handle this problem? So we propose to use the neighboring loss function in the training stage, and then we combine all these loss function together and use this combined loss function to optimize the current codec. So in this procedure, we consider the error the error of current frame on the following frame. So now the learned codec can evaluate the error propagation aware issue. So here we provide some so we can find that compare with the on the GCT-VC design, compare with the class B, compare with the DVC baseline, our approach can save 41% bit rate, while DVC can only save 27 bit rate. So here we also provide some ablation study results. Here the brown line represents the DVC baseline, while the DVC plus OEU represents the online encoder updating scheme. So we can find that our approach bring about 0.5 dB improvement. Furthermore, we also find that we also find the error propagation aware also bring about 0.5 dB improvement for the proposed approach. So in the previous slide, we had talked about how to apply the RDO technique in the inference stage and introduce the online encoder updating scheme. So in this section, I think instead of directly optimizing the encoder, we prefer to generate more options in the learned video codecs and select the optimal mode for each input frame. So as we know that in the traditional video compression, so large block sizes are selected for smooth region, while small block sizes are used in complex regions such as motion boundary. So, but however, in the learned video codec, we find that for the input image, we use fixed optic flow resolution and the motion feature resolution. And basically, they are not adaptive to the video content. So to address this problem, we first need to generate more mode, and which means we have more options for each input frame. In this tutorial, we focus on the resolution of optic flow and the corresponding motion features. Then we will use the rate distortion cost to select optimal resolution for each region. Based on the experience in traditional video coding, we hope that we can use more coarse optic flow for smooth region, like a background region, while we can select a finer optic flow for a complex region. So here is the overall architecture of our resolution adaptive flow coding system. So it still follows the hybrid coding framework and use motion estimation and motion compensation to explore the temporal redundancy. And the residual information will be compressed by using the autoencoder style network. However, there are some differences. First, we propose a RAFC frame modular, which decides global optimal flow maps for each video frame. Then we propose a resolution adaptive block modular, and which selects optimal resolution for each local block of the motion features. So in the next slide, I will introduce how to use these two modular. First, for the resolution adaptive frame block, for example, given we have given ST and ST-1, we feed them to the motion estimation network, and then we can get VT1 and VT2, which represent the most optic flow with different motion, different resolution. Then we feed this two optic flow to the motion encoder and the motion decoder net. Finally, we can get the reconstruct optic flow information. So now in our approach, we have two modes. One is low resolution optic flow map, while the other is a high resolution optic flow map. So how to use this? How to use this two optic flow and then generate different reconstruct frame, and then we can base on this reconstruct frame to generate the RD cost. So basically, we will calculate the RD cost by using different optic flow maps, and then we will select optimal optic flow maps by using the RD cost. So here we further introduce the resolution adaptive block modular in our approach. So now we have in our previous approach, once we get optic flow map, we have to compress the flow information and get the latent features. However, the resolution of the feature are fixed for one input frame. Now the proposed block modular aims to generate latent feature with different resolution and then select the optimal resolution for each location. So there are 4 steps in our approach. First, we use a neural network to generate multi-scale motion features at different modes for each block. Then we will calculate the RD value of different modes for each block. Finally, we will select optimal mode for each block, and then finally, we will merge these two features based on the indicator map. So okay, first I will introduce how to calculate the RD cost. So given the input frame ST and the block A in frame, we use neural network to get the motion feature MT1, and then use error polling to get another motion feature MT2. So now we have two motion features. Then we can use a different motion feature to reconstruct different reconstruct frames. That is ST1 and ST2. So now we can compare ST with ST1 or ST2 and get the rate distortion cost. Finally, we can use this RD cost as a criteria to select the best option for each block. For example, block A in our approach. Then I will talk about how to combine the selected feature in different resolution. For example, in MT1 or MT2 in our approach. So assume the indicator map is provided here. So now we can use the feature as the left part from MT1 and the feature from the right part at MT2. Then we combine this two-part feature and generate the final feature MT head, and then this feature will be used in the decoder side. So this is a overall procedure for our resolution adaptive B-frame comparison, resolution adaptive block modular. So actually we can combine the resolution adaptive frame modular and the block modular. So here we provide some visualization results. We can find that the motion feature with a small resolution are preferred at the complex region such as the motion boundary, while the motion feature with a large resolution are preferred at the smooth region, for example, the background region. So here we provide some experimental results. For example, on the MCLGCV set, our method saves 14% bit rate when compared with H.264, while our method saves 35% bit rate when compared with H.264, while DVC only saves 14% bit rate. So similar results are also observed on other datasets like UAG and the Class E datasets. So, okay. Now I will talk about the enhanced motion estimation. As we all know that the traditional motion compensation procedure, we have the reference frame and the current frame, and we also have an OptiFlow map. Then we will, based on the OptiFlow map, we can get the warp frame by using bilinear function, which can be formulated as follows. So, but however, there are several limitations for this pipeline. First, we need to rely on the existing OptiFlow network architecture, and also sometimes need pre-trained model. Furthermore, since the bilinear warping is not accurate enough, which may introduce more error in this procedure and lead to large residual for the following steps. So how to handle this problem? In this paper, a scale space flow is proposed for learned video compression. So specifically, now they first construct a space volume. So in previous frame, we just warp one frame to another frame. Now they generate multiple reference frame by using the Gaussian kernel. So now we have 3D frames. Then different from previous approach, they also use more dimension for the flow estimation. For example, in addition to the popular displacement field GS and GY, they also introduce the scale field GZ. Then then they will use the scale filter GZ to fuse the information of a reference frame and generate, finally they can generate the interpolated frame as prime. So this formulation is expressed in the following way. So we can find that compared with the bilinear warping, now they can fuse the reference frame at different Gaussian kernel, which provide more robust estimation for the predicted frame. So this overall architecture is approach. So they still follow the hybrid coding framework, and for the R-frame, they use learned image encoder. And then in the P-frame comparison, the input is the reference frame and the current frame SI. Then they use a scale space flow encoder, which will generate the flow information in latent space, and then they use a scale space flow decoder to generate the scale information GZ. Then they use a scale warping to warp the previous frame to current one, and following they use a autoencoder star network to compress the residual information, which is widely used in the existing works. So now we have some visualization results. So here we provide the previous reconstruct frame as SI-1. So we can find that there's an explosion in the center of the image. So it's very difficult to model. Now we can find that the estimated displacement field GS and GY is very similar to optic flow, while the scale field GZ is used to fuse the frame of different Gaussian kernel. So instead of using the bilinear warping, now this scale space warping can reduce the error in the prediction frame, and which means we can have a much better rate distortion trade-off. So here there are some experimental results. We can also find the approach achieves the multipedal performance on the UVG dataset. Okay, now let's talk about the multiple reference frames in the learned video compression. So as we just mentioned, that we can find that existing methods only use one reference frame, as to generate the motion compensation results. So how to explore the multiple reference frame for the learned video compression? So here there are two solutions. First, we can directly use multiple reference frame for motion estimation or motion compensation. And another solution that we can export the long-range temporal information in latent space. So here we introduce one recent work published in CPR 2020, where multiple reference frames are used for video compression. So here the left side is a framework for DVC, while the right side is the proposed MLVC. We can find that they introduced the MAMVP net, which is shown here. So they use this network to get the prediction of a motion vector. So they do not directly compress the motion information. Instead, they compress the motion residual. Here they use DT to represent the motion residual. And then after that, they will reconstruct the motion information. So considering the compression procedure for motion is lossy, so they also introduce the MV refinement to refine the reconstruct optic flow information, which can generate more accurate motion information. Finally, for the residual information, since the residual is also compressed in a lossy fashion, so they also introduce the residual refinement network to refine the residual, so we can have less distortion in the reconstruct frame. So now we give some detail for the network architecture of the MLVC network. So first is the MAMVP net, which is used to get the prediction for optic flow. So we can find that the first input is a series of feature. So they will first extract the feature for optic flow and then use this feature to predict the optic flow or current frame based on the previous optic flow information. Here they use VT-3, VT-2, and VT-1 as the previous optic flow information. So they can get the predict optic flow information VT. Here is VT bar. Then they will encode the residual motion residual. After that, they will introduce the MV refinement network. Similarly, they also use a motion feature from previous frames, and then they concat this feature and go through a DN network, and then we can get the refined optic flow information. Finally, they also introduce the MMC net, which is used to generate more accurate motion information. So in DVC, we only use one reference frame. Here, they use multiple reference frame and multiple reference feature to generate the final predicted frame ST bar, which further reduce the distortion in the prediction stage. Okay, now I would like to talk about another solution that try to using the multiple reference frame. So here is a paper published in RCCV 2019. Basically, this still follows the hybrid coding framework, but I have to say they are totally different from previous approach in to get how to get the motion information or how to compare the motion information. So here ST represent the state, and it includes motion information as well as the residual information. So here the E represents the encoder based on the input, and we will get a bit stream which will decode the state information. So here we can get ST after the decoding. Then we will decode the ST. We will use a generator to generate flow information FT and the residual information DT. So we can get the final information ST hat. So in this pipeline, we can use the previous information in latent space by transfer the state from T-1 to T, and which helps to get much better RD performance. So another work that I want to mention is that from Ren Yang, and so in the previous work, the latent representation generated based on a limited reference frame. Also, the context model also use independent context. For example, when we want to compare the motion information at the current time step, we only use the information in current time step. So now how to handle this? So we can explore the temporal redundancy to generate latent representation and more accurate context information. So here, they propose a recurrent autoencoder. So this encoder can be used to compress motion information or residual information, but the difference is that they integrated the convolutional STM modular into the autoencoder star network. So now, when we compress motion information or residual information at the current time step T, we can get the state information from previous time step, for example, T-1 or T-2. So now we can use the long-term information, which will be helpful to generate more useful features. Here, feature represent the YT feature. So furthermore, in the context model, we need to predict the probability distribution for each feature. For example, YT or YT-1. So in this context model, they also use the convolutional STM. So now we can use the previous feature from YT-2 or YT-3 when we predicting the feature or current time step. So which also help us to generate more accurate probability distribution. Okay, now I will talk about the end-to-end learned B-frame compression. So here, I think first I want to mention that a lot of current approach use a hierarchical architecture for learned B-frame compression. So here, assume that we have 5 frames, and then we can use I-frame compression to generate R0 and I4. Then we can use the B-frame compression to generate I2. And after that, we can, based on R0 and R2, we can get I1. And based on the R2 and the R4, we can get R3. So this is a general architecture for the learned B-frame compression. So now we talk about the paper published in ECCV 2018, where they use the frame interpolation for video compression. So there are several steps in their approach. First, they will extract the feature from the reference frame. Then they also estimate the block-based motion estimation, and they use this information to warp the feature from reference frame to the target frame. Then, based on this feature, we can interpolate the current frame, and then we can compress the residual information using the learned image codec. And finally, the motion information, which we estimated from the block-based method, is compressed by using the traditional image codec. So there are some limitations for the approach. First, this approach is not end-to-end optimized, and furthermore, the motion compression is not learned. They compress the motion information by using the traditional image codec like a PNG or something like that. So in the recent work published in CVPR 2020, RIM proposed a hierarchical learned video compression approach with a recurrent enhancement. So basically, they use different layer for compression, and we can find that as decoder side, the high quality frame will provide a high quality reference to improve the compression performance of other frames. So in the decoder side, we will select the high quality frame from the neighboring frames, and then at the decoder side, the low quality frame can be enhanced by taking advantage of high quality frame, and it is equivalent to reduce the bitrate on the low quality frame. So at the decoder side, they use the recurrent enhancement modular to improve the performance. So so this is a general procedure for the approach. First, for the layer 1, so for the frame at layer 1, they use BPG to compress this image, while for the frame at layer 2, they propose a bidirectional deep compression modular. Basically, this scheme still follows the hybrid coding framework and use motion compensation and motion compression, and as well as residual compression. And for example, given the frame S0 and S5, we can perform the motion estimation to get the motion between 5 and 0. Then we can use the motion compression network to compress the motion information. Finally, they propose use the motion post-processing network to generate the predicted frame S5. And finally, they use the residual compression network to generate the reconstruct residual information. And finally, we can get the reconstruct frame S5C. So this is a basic architecture for the BDDC network. So furthermore, for the frame at layer 3, so they proposed a single motion deep compression network. So as we can see that since there's some relation between the between the motion in neighboring frames. So they try to estimate the motion between S2 and S0, and which can be used to warp the image between for S1. For example, once they get the motion information between frame 2 and frame 0, they can use the inverse operation to get the motion between 0 and 1, as well as 0 as well as the frame as well as frame 2 and frame 1. So now they have two OptiFlow information, which will be used to warp the reference frames S0 and S2. Finally, they still use the MP modular to generate the final predictive frame. And then I would like to also introduce the recurrent enhancement modular. This modular is used to enhance the quality of some low quality frames. So basically, they use the convolutional, use the RSTM modular, and also use some quality gated cell to decide which frame to enhance and which part to enhance. So multi-DL. And okay. I think I just talk about some learned B-frame comparison. Now I think we can find that the previous work used a separate interpolation network and the motion comparison modular. And also the residue is compared in the pixel domain, and it is non-trivial task. So how to handle this problem? And I think one solution is that we can combine the interpolation network and the motion comparison, because as you know that the motion information is only the intermediate information in the video comparison. So we can combine the interpolation and the motion comparison. Furthermore, we can also compare the residual in the feature space. So here in the recent publication in RCCV 2019, the author tried to combine the interpolation of flow compression, and then they can decode these two simultaneously. For example, for the first get, for example, there are 3 frames. S is encoded, S is the current frame, and S1 and S2 are the reference frame. So they first get the OptiFlow F1 and S2. Then the input for the flow encoder are the OptiFlow F1, F2, as well as the warp frame omega 1 and omega 2. So now, as the decoder side, they generate the reconstruct of OptiFlow F1 head and F2 head. They also generate the coefficients F1 and F2. So now we can interpolate the intermediate frame by using the following formulation. So where this information can be decoded from the decoder without considering other constraints. So now it's about how to compare the residual information in latent space. So here I'll give some example. For example, once we get the predicted frame as interpreted and the original frame X, so we can use the CNN network to extract the feature in feature domain. Here, we use a feature extractor to get some feature Y and Y interpret. Then we can get the feature residual between these two features. Then this feature residual will be compressed by using the entropy coding tool. Finally, they will use to reconstruct frame ST head. Okay, next I talk about the learned autoencoder based video compression. So, okay, so I think today I have talk a lot of work about hybrid coding framework. Now we all know that this framework uses motion estimation or motion compensation or residual coding, and they also use OptiFlow network to estimate the motion information. And sometimes they have to compare the motion and the residual information separately. And so in this paper, I also propose a more simple solution for video compression. They directly use 3D convolution, 3D autoencoder to compress the video frame without motion estimation. For example, here the input is a chunk of videos, and then they use some red block-based 3D autoencoder to extract features for this video sequence. After that, they use a decoder to decode this video sequence. So to enhance to improve the comparison performance, they also propose autoregressive prime model, which is shown in Figure C. You can find that to predict the probability model for current frame, the probability model is conditional on previous latent space. So here, the experimental results show that they can achieve a better performance than DVC in terms of multi-scale SSM. Okay, now I will have some discussion for the benchmark and benchmark results are our recent open source project. So today I will talk about a lot of learned video comparison method. So I think here we make some comparison between this. So we use GCT VC dataset, including class A, B, C, D, E, and as well as UVD, MCL, and VTL dataset. So these dataset are widely used in the existing works. So we also select H264 and H265 as our anchor algorithm, and also we use 7 learned video codec here. And it should be mentioned that the PSR is calculated in the ITV space, and also we use X264 or X265 as the default in the default mode to generate the comparison result for H264 and H265. So the DOP size is set as 10 or 12 for different this set. So here we can find that the baseline for the different data set, the different method has its own advantage. For example, on the class B data set, the DVC plus has achieved the best performance. In the DVC class, they use autoregressive prime model, which show much better performance. While for the class E data set, the method proposed by Hu show much better performance because since the class E is a conference scenario where there's a lot of background region. So the method in Hu use resolution adapted flow coding, so which improves the performance significantly. Okay. Finally, I will also talk about our recent open source project. So just in the previous tutorial, Ren just shared some very interesting open source project. And now I would like to also introduce our recent PyTorch data comparison repo. So in this repo, we will provide the learned image comparison, learned video comparison, as well as the learned protocol comparison method. We have implemented some baseline method, including Ballet's work in RCR 2017 and 2019. And also we will release some source code for the autoregressive prime model published in VCIP 2018. As we already released source code for DVC published in 2019. And we plan to release other baseline method in the future. So here is the reference in this tutorial. Finally, I have to thank for the co-author Chunli Cai from SDQ and Zhihao Hu from Beihang University and Chris from USYD. I have to say thanks for Ren Yang and Chao Yuan to provide their experimental result for the benchmark data set. Okay, that's all. Thank you.
Okay, we have some time for Q&A session. So again, if you have questions, please use the chat bar, and then let us just enter your question and let us know. So there is a first question. In the training, we adjust the weights at encoder and the decoder, but the encoder OP values will be IP output value will be the input value to decoder. So which learning is best to minimize error function in video compression network models? Just wait.
Sorry, I don't get mean the encoder OP value will be input to the decoder.
No,
Right.
I think in our object function, we minimize the reconstruction error and at the same time minimize the number of bits used. We have rate and distortion, two terms. Distortion, we use the predictor from Google. We can predict how many bits will be used for entropy coding. But for the distortion, it's very easy. We just do the reconstruction. For each input image, we need to go through this encoder and decoder, and then we got the reconstruct image. And then we compare, we calculate the error, the L2 error, or the MSE, the MSE error, or the MS-sim error similarity between the reconstruct image and the ground truth image, original input image, and then we got the error for each frame. And then after we finish the process for all the frames, we got the total error for the whole video. And then we minimize the total loss from the whole video, as well as minimize the estimated bits from the network, bit estimation network. So that's the basic idea. I hope we answer your question. Yeah. Compared with HEVC, what's the performance of the current end-to-end methods? Yeah.
Okay. So if we want to compare our approach with some, for example, HM or the VTM, so I have to say that the current state-of-art mass learned approach cannot compete with the HM or the VTM approach. Okay. So, but if we compare in other settings, such as we use S264, S265 as our anchor method, so I think we can have a very similar or better performance than X265. Okay.
No, I think in some settings, we already, our recent work submit to CVPR, we already achieved comparable results on HEVC class E dataset, right? And the VTC dataset, right? Which means that when the background is in the video conference scenarios, our method can already achieve some competitive results compared with H.265 HM, the best model of H.265. But in general, in class B and class C, in some rates, at some bit rate, we are close. But at the most bit rate, we are still some gap. Yeah. Lugo, am I right?
Okay. Why there's error propagation in deep video compression? So I think the reason is that one thing that I want to mention, the difference between traditional video compression and the learned video compression is that in the traditional video compression, we will use the RDO technique in the reference state. So even there's some quantization error or something in the previous frame, we can select or can still select the best, the optimal mode in the inference state. So the error propagation issue is not very serious in the traditional video compression, but for the learned video compression, since we do not have this scheme, so I think this problem will have a lot influence on the final compression performance. So I say that you mean that we can get the correct residual. Yes, we can get this, but considering that the previous frame has some error information, I mean some distortion. So we may need more bit rate to get this residual information, which lead to poor RD performance. Okay, I think I hope this can answer your question. Could the slides be available? Yep, we all submitted this to the organizing tutorial chair, and we all upload this these slides to our website. Okay. I know that a lot of people are curious about the complexity. So actually, we try to get some number for this. So basically, for the class B dataset, when we evaluate it on the GPU platform, the encoding speed is about 1 FPS by using GPU platform. So okay.
Oh, hello, Dr. Lu.
Hello.
Hi, nice to meet you. So yeah, this is Hamilton from Waseda University.
Okay.
Yeah, thank you so much for the interesting talk. So could you please pardon, so which kind of the resolution did you mention just?
Okay, I use the class B. I use the class B dataset for evaluation. So the resolution is about
2K by 1K.
Yeah, 2K by 1K. Yeah.
So 2K by 1K by using maybe a powerful GPU.
Yep. Yeah.
So
yeah. We use a 2080 Ti. Yeah.
It can achieve around 1 FPS.
Yeah, 1 FPS.
Thank you so
much.
So
the decoding will be a little faster, but at the same level, I think.
Also around 1 FPS.
Yeah.
So still for the class B sequences.
Yeah, class B sequence.
With the same level GPU. So 2080 Ti or something.
Okay, yeah.
I see, thank you. So could I ask one more? So there's another question. So
yeah, how about training time? So to train the DVC framework, we need about 5 to 7 days to train the whole model from the scratch. But I have to mention that if we want to fine tune to other model, it's much faster. It only takes about 1 day or 2 days. It's much faster. So
I think Sun Heming wants to ask another question. Go. Yeah.
Okay.
Could I ask just by talking, or should I ask by chatting?
It's up to you. It's up to you. It's
okay.
fine.
So on slide 14.
Slide 14. Okay. Sorry. You mean slide 14, right?
Yeah, 14. Not 40. 14. Oh yeah. Oh, thank you.
Okay.
For one page before.
Okay.
Yes.
Okay.
Yeah, thank you. Yeah, so I didn't get the point for this subfigure C, D, G, H. What do you want to say? So by the comparison of the subfigure G and H.
Okay. So for example, for the figure C and figure D, we provide the visualization of the feature before and after the updating. So we can find that there's some difference after this updating. And
yes.
For example, we can find that since the yellow color represents the high intensity, while the red color represents the low intensity. So we can find after the updating, some region changed, and also for the flow information, for example, figure E and figure F, we can find that there's some new more detail in the flow in the motion boundary. For example, in the human in the motion boundary of the human. So I think it's just a visualization of our approach. And if you want get some more information, I think we also provide the PSR results and the BPP results. Okay.
So can I understand that after updating or after using your proposal, maybe some bits will be more allocated to the important part in image or something like that? No, not like that.
I'm not quite sure about this. Yeah, I'm not sure. Okay.
I see. Okay, thank you.
Thank you for your question.
Do you have any questions? Yeah.
This video be available online later? Yeah, I think so. Yeah, this video will be available for the registered VCIP audience. Do you think optic flow estimates are necessary for video compression? Currently, I think most approach, including paper published in including the learned P frame or the learned B frame approach, all use the optic flow information. So I think it's actually very important to use optic flow to exploit the temporal information. I also noticed that there's some paper, yes, as we show in the learned autoencoder based network, where we just use where the author just use autoencoder instead of optic flow to compress videos. But I have to say that in our experience, we find that if the motion is not very large, I mean the motion is very simple or the magnitude is very small, we can use autoencoder based method. But when you're handling some very complex scenario, I think optic flow is very necessary.
I think in our recent work submitted to CVPR, we do not use optic flow estimation at all. We have a totally new framework which can fully replace DVC. Once this paper is published, we will announce it. Any other questions from the audience?
Yeah, so can I ask one more question?
Yes, please.
Sure.
Yeah, so page maybe 45 or something.
45?
Yes,
okay.
yeah, so you mentioned that so you do the enhancement at the decoder side for several frames.
Yes.
Maybe in Dr. Ren's CVPR paper or something.
Yeah, maybe Ren can answer this question.
Yes.
Yeah, so
what is the question?
my question is so for different okay, so can you go to 45? Yes, so for different frames, so here, for example, frame 1, 2, 3, 4.
Mm-hmm.
So you utilize the exactly same network to do this enhancement, or different kinds of the networks to do this enhancement?
Well, the enhancement network is a recurrent network. And could you please go to the following pages, Guo?
Okay.
To the enhancement network.
This one.
Yes, the key point for the enhancement network is that there is a weights generator. Well, so first the answer is yes, the enhancement network on all frames are the same, but there's a weights generator, and the input to the weights generator is the quality and the bit rate of the current frame. And this information is input to the quantity gated LSTM cell. So please note that this green cell is not a standard LSTM cell, but its forget and update gates are weighted by the output of this weights generator. And therefore, the key point here is that, for example, the current frame has very low quality, and therefore we want to use its high quality neighbors help to enhance the current quality. And in this case, the update weight will be set to be very small. This WS will be small because its quality is very low, so we do not want to update its information into the memory because it's not helpful for other frames. And at the same time, we want this WM to be large because we want to maintain the previous information in the memory because they are very helpful to enhance this low quality frame. And
so, please go ahead.
Yeah, and if this frame is a high quality frame, and we want to update its information to the memory and do not want its previous information have any effect on this frame, and therefore we will set WM to be small and WS to be large.
So these frames can be enhanced in parallel.
It's not in parallel because it's a recurrent cell. So we still need.
Okay. So in the maybe slide 45. So for example, slide 45.
45.
Yeah, 45. So here reference. Could you see my notation here?
What notation?
No. So
no.
I make some notation on the screen. No.
Okay. Yeah.
Oh, see. So this, for example, frame 1, 2, 3, 4. They are enhanced. They are enhanced one by one.
Yes, from 0 to 10, one by one. Yes.
I see. So also for this keyframe, for example. Frame,
No. And no. Another thing is it is a bidirectional recurrent network. So actually they are the output are the same at the same time because it's a bidirectional, one cell from 0 to 10 and one cell from 10 to 0. So the output will be obtained at the same time.
Output, you mean the output for these 11 frames?
Yes.
Okay.
Because it's a bidirectional recurrent cell.
So even though for the keyframe here, for example, frame 0, frame 5, and frame 10, you still do the enhancement.
Yes, it's something like a single frame enhancement, just like similar to the enhancement of JPEG image and so on.
For example, loop filtering or something. Just a filtering for a single image.
Yeah, something like that, but it's learned. Well, and the key point of this whole method is that we manually design this 3 layers hierarchical framework, and therefore the frames 1, 2, 3, 4 have very low bit rate. But because of the high quality in frame 0 and 5, the frames 1, 2, 3, 4 can be significantly enhanced by our recurrent enhancement network at the decoder side by using the high quality information in frames 0 and 5. And therefore, in this solid line, we can see that the frame 3 and 7 has almost a similar quality to frame 9 to frame 5, but with much lower bitrate. So it is equivalent to reducing the bitrate on low quality frames.
That is quite clever. So you mean so you reduce the bit consumption for the frame, for example, 1, 2, 3, 4 here, but you just enhance the quality of these frames by utilizing the relationship between, for example, frame 3 and frame 5 and frame 3 and frame 0, right?
Yes, exactly.
Oh, I see. I got it. Okay. Thank you. Thank you so much.
You're welcome.
So I have uploaded the slide to the Google Drive, so maybe you can use it. So I think we can end this session.
Okay. So thank you for all participants attending this section. If you have no questions, I will end this section. Thank you for attending. Thank you for all speakers for this section. Have a nice day.